will cover section 3.5, double angle and half angle identities. So we've made it to the last section of chapter 3. We're learning the last two groups of identities. And at the end of the section, we'll have 10 groups of identities to work with to complete the chapter 3 problems. Okay, so the first one here, we derived it in section 3.4. So we're able to use the sum and difference identity for sign to expand the left side, transform it into the right side. So this was derived in section 3.4. For cosine double angle, so double angle means the input is 2x. There are 3 different formulas that are equivalent. And then for tangent double angle, we just have 1. So cosine double angle is the special one. It has 3 variations. And the way that I learned them was by the names. The first one, so they each had names, and you use the one that's most appropriate for your given problem. So in your problem, if you need both sines and cosines, that's the first one. So that's the traditional one. We use the traditional flavor vanilla. Nothing exciting, but it's the original flavor. Cosine of 2x is equal to cosine squared x minus sine squared x. Okay. The cosine double angle identity that contains just cosine, C for cosine, C for chocolate. So that's our chocolate identity. The cosine double angle identity that contains just sine, sine starts with S, strawberry starts with S. And so we have these 3 ice cream flavors to represent our 3 double angle formulas for cosine. In your proof, if you need both sine and cosine, use vanilla. Later on, when we get to solving equations, if we want everything in terms of cosine, use chocolate. Everything in terms of sine, use strawberry. So all 3 are equivalent, but we choose the appropriate one given the problem. Okay, so sine of 120 degrees and cosine of 90 degrees, these are on the unit circle. But for practice, we're going to use the double angle identities to get the exact value. Before we do that, students, can you put in the public chat, what is sine of 120 degrees and cosine of 90 degrees? Based on your unit circle knowledge, share in the chat. So put your answer for sine of 120 degrees first, and then cosine of 90 degrees. So you need to visualize what is the y coordinate at 120 degrees? What is the x coordinate at 90 degrees? Visualize that on the circle. That will give you the answer for these 2. For participation, please share in the public chat. Okay, thank you, Genesis, for starting us off. Are we in agreement with Genesis? Genesis is saying that sine of 120 degrees is positive root 3 over 2. Stephanie agrees. Cosine of 90 degrees is 0. Okay, and then remember the exact value of trig functions. They are ratios of x, y, and r, so there's no units. Okay. For what I'm seeing, we're in agreement for the most part. Yes. Okay, thank you for clarifying there. Very good. So we already know the answer, but this time we're going to practice using the double angle identities in the same way we use the sum and difference identities. Okay, there's a 3-step process. Go back in 3.3 to check the 3-step process we put in a note card. Step 1, rewrite the given angle this time as 2 times a unit circle angle. So 120 degrees is 2 times 60 degrees. And we have to choose an x that's on the unit circle. So x must be on unit circle. 60 degrees is on unit circle. So 120 degrees is double 60 degrees. That means we can use the double angle identity. So step 2, apply the appropriate identity. Sine of 2x, that's going to be 2 sine of x cosine of x. We derived that in the previous section. Okay, so 60 degrees, at that angle measure, we have short leg, long leg. Sine is the long leg, root 3 over 2. Cosine is the short leg, 1/2. Okay, 2 divided by 2 is 1. And so our answer simplifies to root 3 over 2, which matches what we know for sine of 120 degrees. Okay. Next one, let's follow the 3-step process. Step 1, rewrite the given angle as double a unit circle angle. 90 degrees is 2 times 45 degrees. Now we're going to apply an appropriate identity and then evaluate and simplify. Those are the 3 steps. Step 1, rewrite given angle. So rewrite given angle, either sum or difference of unit circle angles or double the unit circle angle. Step 2, apply the appropriate identity. Step 3, evaluate and simplify. So we have options here. Let's use vanilla. So the vanilla formula is cosine squared of x minus sine squared of x. So we're using vanilla. Okay, so at 45 degrees, both legs of the triangle are root 2 over 2. So that means cosine and sine are both root 2 over 2. So we have root 2 over 2 squared. That's going to be 1/2. Anything, so 1/2 minus 1/2 is 0. That matches. When you're writing out the solution, make sure you specify between degrees and radians. When your angle measures in degrees, you must have the degree symbol. When your angle measures in radians, there should be no units. So if you wrote on your exam sine of 60, this means 60 radians. If you intend to write sine of 60 degrees, you have to have the degree symbol. So that detail is necessary, important. Okay. Any questions with page 1? If we don't have questions, let's just put a G for good to move forward. The next problem is a little more challenging, but an important one. Okay. Thank you, students. Collegian Genesis, Miguel Jacob, Stephanie, Esmeralda. Okay, so if we didn't put in a G, good to move forward, are there any questions with this first page? Okay, see Juan, Hector, and Justin are good to move forward too. And Stephanie, thank you. Okay, so then you're seeing how we can use the 3-step process to find the exact value. Applying identity groups, this was 5, 7, 8, 9. Step 1, rewrite given angle as either sum or difference of unit circle angles or double a unit circle angle. Step 2, apply appropriate identity. Step 3, evaluate and simplify. Moving to our proof, let's also double star this one. This proof is a really good one for us to review. Okay, so for this type of problem, I would encourage us to use the apple banana method. But so first, let's work through it together. Okay, so although the right side looks like there's more steps we can take, the left side, when you have sine of 3x, you're able to expand that. So assessing both sides, it looks like it would be easier to go from left to right than from right to left. Okay, so we're going to go from left to right by expanding the left side. Okay, so the left-hand side, that's sine of 3x. We're going to rewrite 3x as, it says, write it as 2x plus x. Okay, so when you have sine of alpha plus beta, you can expand it using identity group 7. So that's our sine sandwich. Goes as follows. Sine of alpha plus beta is sine, cosine, cosine, sine. Okay. And I'm going to write it a little more spaced out. You'll see why in a moment. So it's sine, cosine, cosine, sine. The first angle is 2x, second is x. First one is 2x, second is x. Okay, so we rewrote 3x as 2x plus x. Next, let's see if we could apply double angle identity. So sine of 2x, we could apply double angle identity. And cosine of 2x, we could apply double angle identity. For sine of 2x, we know that's 2 sine x cosine x. Okay. For cosine of 2x, we have 3 options. When we look at our ending right-hand side, our right-hand side has both cosine and sine. So I would think that vanilla would be the best option. If the right-hand side was all in terms of sine, we'd use strawberry. All in terms of cosine, we'd use chocolate. But this one, our ending expression should have both sines and cosines. So let's try vanilla. Vanilla formula tells us cosine of 2x is cosine squared x minus sine squared x. Okay, so all we've done so far is apply identities. Group 7 and group 9, we expanded sine of 3x, and then we substituted sine of 2x and cosine of 2x with the double angle identities. Because our final destination right-hand side, the input should just be x. Okay, so at this junction, this is where it may be helpful to use the apple banana method. Okay. So the apple banana method goes as follows. We see here our expression has both sine and cosine. So let's let apple be sine, banana is cosine. Okay. So that means right here where I put a star, right here where I put a star, if we rewrite this expression that looks maybe intimidating, in terms of A and B, this is what we have. This is 2AB times B plus, this is B squared minus A squared times A. So we rewrote line number 4 in terms of A and B. We replace sine of x with A, cosine of x with B. Okay, so now let's go to Stephanie. Stephanie, we want to simplify this expression. Okay. However, we want to simplify it in a way that matches the right-hand side. Any ideas?
We could distribute the B and the A.
Yes, we could distribute, but looking ahead to the right-hand side, notice that they have a sine of x that's factored out.
Oh, that's right.
Yeah, so let's pull out an A. If we pull out an A, Stephanie, what's left inside?
That
So
would be,
pull out an A from the first term.
so it'd be 2B squared.
That's right. Pull out an A from the second term.
That would be B squared minus A squared.
Yes, that's right. Okay, so we're factoring out an A from the first term, an A from the second term. We're pulling that out. First term, when we pull out the A, we have 2B squared. The second term, when we pull out an A, we just have B squared minus A squared. Okay. And then Stephanie, help us continue. What are the like terms now?
That would be 3B squared minus A squared.
Yes, 2 banana squared plus banana squared. We have 3 banana squared minus apple squared. Okay. And is this expression matching the right-hand side?
Yes.
Yes, it is. So thank you, Stephanie. We're able to use the apple banana off to the side to guide us. Now let's go back here. So the apple banana method showed us that in order to arrive at the right-hand side, we need to factor out apple, which is sine of x. So let's pull out sine of x from the first term and from the second term. The two terms are divided by an addition sign. So when we pull out sine of x from the first term, we get 2 cosine squared x. Pull out sine of x from the second term, we get cosine squared x minus sine squared x. Then we saw from the apple banana method that the 2 cosine squared x and the cosine squared x are like terms. So we're able to combine like terms. We have sine of x on the outside times in brackets 3 cosine squared x minus sine squared x. And yes, indeed, we do get an expression that is equivalent or that matches the right-hand side. So we've shown that our left side is equivalent to the right side. Okay, take a look and ask questions.
Um, is there any particular reason why you use brackets?
No, it was just because there was so many parentheses, it was a little more clear to see it that way for me visually.
Okay, thank you.
Mhm. Oh, I guess because I always like to put parentheses around the X for clarity. So you could use parentheses or brackets. Either way is fine. These are the types of problems that you want to practice from the textbook, showing that one side is equivalent to the other side. The tools that you have to work with are the 10 groups of identities that we will have at the end of this section. And in general, when you see squares, you want to think Pythagorean identity. However, always keep your eye on the final destination. So if you start on the left side, the final destination is the right side. If you start on the right side, final destination is left side, because that's your goal. That's what you want to transform your expression into. Okay, I'm pausing because I want to check to see if there are any questions. Okay, I think we're ready to move down to group 10. So I'll tell us that for group 9 and 10, these are identities that I know when I'm teaching trig or taking trig, but they're ones that you may not necessarily store to memory long term. So you definitely want to put them on your reference guide. Okay. The reciprocal identities are ones that you want to store long term. Pythagorean identities, yes. Sum and difference identities for sine and cosine, yes. Tan and cotan. But for these very specific ones, double angle, half angle, we can actually derive them. So anything we can derive, you don't necessarily need to store to memory, but we should have them in one page to use as reference. Okay. And how we choose, I'll draw attention here. How we choose the plus or minus sign is based on what quadrant the angle lies in, as always. If you're noticing repeatedly that you're getting an answer wrong because you're missing a negative sign, that's telling you you need to check the quadrant for your input. The quadrant for your input will tell you whether the trig function is positive or negative. Okay. We're going to skip the top one and go down to the bottom. We want to find tangent of 3 pi over 8. So 3 pi over 8 is not on the unit circle. When the given angle is not on the unit circle, and you want to find the exact value of the trig function, then we need to pull out that 3-step process. So we can rewrite the angle as sum or difference of UC angles, or either double or half of a UC angle. Okay. So if we do some scratch work, 3 pi over 8, that's half of 3 pi over 4. 3 pi over 4 is a unit circle angle. So we can treat that as x. Remember, x must be a unit circle angle. Must be on unit circle. Okay, so just doing some scratch work, we see that 3 pi over 8 is half of 3 pi over 4. Okay, let's see. So because we make that observation that 3 pi over 8 is half of 3 pi over 4, then we can use a half angle identity. So rewrite your given angle, either sum or difference of UC angles, or double or half of UC angle. This time 3 pi over 8 was half of a UC angle. And Step 2, apply the appropriate identity. Okay, so going back up here, for tangent of half x, we have 3 different options to use. Let's use this third option here. It looks the friendliest for our problem because the denominator is just one term. But you can use any of these options, it's fine. Just remember that you want to rationalize your denominator. So I chose the one that maybe would be easiest for us to work with the denominator. Okay. So our identity, number 3, tells us tangent of half x is 1 minus cosine x over sine x. So this was one of the half angle identities. Okay, so let's go ahead and apply that half angle identity. Tangent of half x is equal to 1 minus cosine of x divided by sine of x. You have to pick the x that's on the unit circle. And 3 pi over 4 indeed is on the unit circle. Our given angle is half 3 pi over 4. So we're good. Okay, so Esmeralda, what is cosine of 3 pi over 4? Esmeralda, is your mic working? Please. Oh, go ahead. What is cosine of 3 pi over 4? So 3 pi over 4 is in the 45-degree group. What is cosine of 3 pi over 4? Okay, Esmeralda, I'm not able to hear you.
What about now? Hello?
Go ahead.
Okay, so I said it again. Negative square root 2 over 2.
That's right. Good. The 45-degree group, the legs are both root 2 over 2. 3 pi over 4 is in quadrant 2. So your cosine value is negative. And then sine of 3 pi over 4 should be positive root 2 over 2. Thank you, Esmeralda. Okay, so Stephanie reminded us that 1 can be rewritten as 2 over 2. And when you're subtracting a negative, you're adding. So let's remember all of our algebra skills. Subtracting a negative means you're adding. Okay. So we have 2 plus root 2 divided by 2 over root 2 over 2. Fraction divided by a fraction, we do top fraction times reciprocal of bottom fraction. 2 divided by 2 is 1. And then now we want to rationalize the denominator. So our denominator here is a single root 2. Let's multiply top and bottom by root 2. Okay, so we have 2 root 2 plus 2. This is when we distribute. 2 root 2 plus 2 over 2. 2 divided by 2 is 1. 2 divided by 2 is 1. So we end up with square root of 2 plus 1. Okay. So to find the exact value of a trig function, evaluate it at an angle not on the unit circle. use the three-step process. Rewrite your given angle as either sum or difference or double or half unit circle angles. Then apply the appropriate identity to expand your expression. Last step would be to evaluate and simplify. To check our answer, students, let's put in our calculator. What is tangent of 3 pi over 8? We need to be in radian mode this time. Let's share in the public chat. When we go in radian mode, what is tangent of 3 pi over 8? So please share in the public chat, part of your participation. Okay, so I'm putting it in my calculator. I'm getting 2.414, same. Very good. 2.414. When we put in square root of 2 plus 1, we also get 2.414. So this is a nice way for us to check our answer. Okay, I'm going to say this so we're aware that on an exam, if it says whether this is through My Math Lab or free response, if it says find the exact value, okay, and you answer with the decimal, that would be getting 0 points because the decimal, the calculator can do that. Finding the exact value requires us to use our trig and algebra skills. So an answer 2.414 would get 0 points. You have to show your work for applying the three-step process to get the exact answer. The 2.414 is only for you to check your answer, but your final answer must be in exact form. So anytime it asks for exact form and you give a decimal, you would not receive credit, as the decimal values you can get using your calculator. The exact values require our trig and algebra skills. And that's going to be true as you move forward into calculus. When they ask you to find derivatives and integrals, if they ask for exact value and you give a decimal, you would not be receiving credit. Okay. So what we have remaining in 3.5 is we have 2 proofs, and then the last 2 problems are double star ones that you'll definitely be seeing on the exam too. So our plan for today is we're going to go work on the proofs in the breakout rooms, go through those solutions, and I think we'll wrap for today. Tomorrow we will wrap up chapter 3 and start chapter 4. So have those notes ready tomorrow. Okay. So we have 2 proofs to work on. These ones I'd say are maybe a little more challenging than the 2 we did before the break. Use the apple banana strategy if necessary. And make sure that when you're doing the proofs, you are showing all the steps, and from one line to the next, it's equivalent. So if there are steps in between that are not equivalent, then you'll be getting deduction. We know the goal for the proof is to start from one side to the other side. The grading comes in the work, your solution, how you get from one side to the other side. Okay. So these problems do not have a lot of steps, but important steps. So you're going to start on one side, either left or right, transform it into the other side. Remember, if that method isn't working for you, you always have the option to simplify both sides to show that both sides simplify to the same expression. but start by trying to transform one side into the other side first. If that doesn't work, then you can use the alternative approach. Are there any questions? Jimmy, no problem. We can actually do that while students are in breakout rooms. So in breakout rooms, you're going to work on these two proofs, number 1 and 2. Your goal is to be able to, as a group, transform one side into the other. We'll be going through the full solutions as always, but try on your own first. I'm going to pause the recording while students are working in breakout rooms.
Recording stopped.
Okay. Are there any questions before we go into the rooms? At this point, we have 10 groups of identities to use to help us with the proofs. Okay. So Jimmy, stay in the main session. Everyone else, let me open the rooms. Go back to your breakout rooms to discuss these two.
You guys gonna start on?
I'm starting off on the left side. I'm taking a second power out. So it's going to be cosine squared alpha parentheses. That's going to be squared minus sine squared alpha. That's in parentheses, and then sine squared is squared. So then you can do factoring, which is that's technically a squared minus b squared. So it'll come out to x squared plus y squared parentheses, well, cosine plus sine squared parentheses, and then cosine minus sine in parentheses. They're both squared. Make sense?
For the most part, yeah.
All right, cool. I can show you my screen if you need. And then you can further factor the cosine, and then that turns into other stuff, but not all the way there yet, though. Because that's technically. I know, because then that turns into. Oh yeah, because then cosine squared minus sine squared breaks out into cosine plus sine parentheses sine minus sine parentheses, which is one of them turns out to be 1. Yep. Because cosine squared x minus sine squared x is cosine 2x for the double angle identities. And then cosine squared plus sine squared is 1 as well for the Pythagorean identity. Or actually, no, technically you can just leave it cosine. Oh, wait, no. Yeah, never mind. I was right. And then you got to break it apart again. Cosine squared plus sine squared. And then that's going to be cosine squared alpha. Sine squared alpha. And that's 1. So it's cosine squared. So you guys want me to show my screen? Or are you good?
Can you please share?
See how I took out the first to the second power, so then it made it cosine squared alpha I don't know, let me see, plus sine squared alpha, or no, minus, and then that's squared, and then that's a perfect square, so then it comes out to the second one, and then this right here is equivalent to 1. That's a Pythagorean identity. So then that's a 1, and then yeah.
Awesome. Thank you.
You're welcome.
Hi, students. How are we doing with these 2 proofs? Any questions?
We just finished the first one.
Okay. Are we in agreement with the solution?
Yeah.
Yes.
Yeah.
Okay, very good. Thank you. Keep working, and if you have questions when you're in the breakout room, you can always hit the ask for help key and I can come in here. It may be helpful for both of these off to the side to rewrite sine and cosine as A and B. Use that method if it helps you. Okay, I'll be in room 2. Let me know if you need help.
Anybody have any thoughts on the second one? Okay. Okay, cool. I'm just keep me posted.
Okay, so what I've done so far is that I did I just wrote out sine x minus cosine x and then the same thing because it's squared. And then I multiplied everything together, so I got sine squared x minus 2 cosine times time, I mean sine, plus cosine squared x. And then because they're all added together, you can use the commutative property to bring sine squared x plus cosine squared x together, and that would just equal 1, right? And then you have 1 minus 2 cosine sine.
Yep, you're
And that's
right.
what I'm stuck on.
Well, that's no, you're good because then it's 1 minus 2 cosine. Oh, my bad. So the other side, the way I proved it, I already did that part. I did 1 minus, and then I used the double angle identities. So sine 2x actually comes out to 2 sine x cosine x, which is exactly the left side that you just did.
Oh, so you simplify like both sides?
Yeah, I did both sides. I
Okay.
did the other side, but by you doing the left side, it
It
proves
makes
my
sense. Okay.
Yeah.
Yeah, okay. That makes sense now because I was like, I didn't know what else to do. Okay.
I think that's why I was getting stuck too. I
Yeah.
was just focusing on one side. Sweet.
There, yeah. So then that's done.
Yep. We proved it. Like it. It was only those two, right?
Yeah, only those two.
I see that we're back, so we're going to hear from both groups. Let's resume the recording.
Recording in progress.
Okay, so let's start with our group 1. We had Hector, Jacob, Justin, Kalita, Miguel. So let's hear from Jacob. Jacob, which side did you start with, and how were you able to transform it into the other side? Jacob, go ahead and.
I was on mute.
Okay, yeah, go ahead.
So we started with the left side, and so we broke it up from cosine root. Cosine to 4 over 4, then minus sine 4, to cosine squared times. Cosine squared a, then squared again because it's in parentheses, minus sine squared in parentheses squared, and then
Okay.
from there.
That's close but not correct. So let's make an adjustment there.
We took out a 2 from the roots, from the powers. So then it would be cosine squared to the second power, and then sine squared to the second power, and then that breaks out into cosine squared plus sine squared in parentheses, and then cosine squared minus sine squared. That entire thing is squared.
Okay, I think I'm following, but so when you show it, you're not really removing a square. I
But
think
you're
I
just-
I,
it's
I
still
understand
the-
what you're saying. Mhm.
Yeah.
So students, some of you that may have difficulty with factoring when you have trig functions, the apple banana method may be helpful here. So let's let A be cosine of x, B be sine of x, or actually A is cosine of alpha, B is sine of alpha. So when you have A to the 4th minus B to the 4th, this is a difference of 2 squares. So I think what Jacob and Justin were saying, they rewrote it as A squared squared minus B squared squared. Is that correct?
Yep.
Okay, so when you have a difference of 2 squares, it's going to be first minus second times first plus second. First being the first would be the A squared, second would be the B squared. So when you have a difference of 2 squared, variable squared minus variable squared, it's going to be first variable minus second variable plus first variable, times first variable plus second variable. I'll write it out here for us. So if you had, let's see, we'll use different letters. So x squared minus y squared, that's x minus y times x plus y. So in our problem, it's a squared minus b squared times a squared plus b squared. Okay. Great. So that side work helps us out perhaps expand. So here we have cosine squared minus sine squared times cosine squared plus sine squared. Let's go to Hector. Hector, when you see cosine squared plus sine squared, what is that equal to? Okay, can someone in group 1 step in?
It's 1.
1.
That's right. The reason why it's 1 is because on the unit circle, cosine is the x leg, sine is the y leg. The unit circle, the hypotenuse is 1. So leg squared plus leg squared is hypotenuse squared. Thus, cosine squared plus sine squared is equal to 1 squared, which is 1. Okay, so this part is 1. And then the other portion is our new formula, our vanilla formula, cosine of 2 alpha. Oh. Oops. So this is vanilla. Okay. So then it simplifies to just cosine of 2 alpha, which is the right-hand side. If we try to start with the right-hand side and use identity group 5, we're going to hit a dead end. So when you're doing these proofs, you might not be able to arrive at the other side on the first try. You may go down different paths, but know that you do have the 10 groups of identities to use to transform one side into the other. Does anyone have a question with our algebra steps, how we factored here? Difference of two squares, x squared minus y squared is x minus y times x plus y. In this problem, our x was cosine squared, our y was sine squared. Okay. Now, group 2, did we also get the same solution? Transforming left side to right side. Please share in the chat. Great. So Genesis said yes. Thank you, Genesis and Stephanie. Stephanie, take us through what your group did for number 2. How do we transform one side into the other? And which side did you start with?
Started with the left-hand side.
Okay.
Use apples and bananas to simplify.
Okay.
So sine is equal to A, and then cosine is equal to B.
Mm-hmm.
So the equation is transformed into A minus B in a parentheses, all squared.
Yes.
Expanded, that equals to A squared minus 2AB plus B squared.
Okay, let's pause there. So when you have a binomial squared, a very common mistake is students will say this is a squared minus b squared, and that's not correct because we cannot distribute the exponent. We could distribute factors, but we cannot distribute exponents. So it may be helpful to rewrite a minus b quantity squared as a minus b times a minus b, which allows you to distribute a squared minus AB minus AB minus B squared. Okay. I would encourage you, especially if those algebra skills are a little rusty, for you to rewrite your trig functions as A's and B's, which does help with distributing and factoring. Okay. So with that, before we move forward, let's go ahead and write our proof. The apple banana is really our side work. Our proof has to include sines and cosines here. So when we expand the left side, we get, this is sine squared minus 2 sine cosine plus, cosine squared. So we're able to expand, and sine of x minus cosine of x quantity squared is equivalent to sine squared of x minus 2 sine of x cosine of x plus cosine squared x. Okay, Stephanie, what is the next step here?
The next step that I did was I saw that there's a sine squared and a plus cosine squared in the equation. So according to the Pythagorean theorem, sine squared of x plus cosine squared of x is equal to 1.
That's right. That only applies if there's a plus. So if it was a minus, then you'd have to look at the other identities. So because this is sine squared of x plus cosine of cosine squared x, that is 1. Okay, good. Very good. And then Genesis, what's the last step here?
I actually didn't finish this one, but
Mm-hmm.
let me look at the.
So look at your reference guide to see, do you find 2 sine of x cosine of x?
Equal to sine of 2x.
Very good. Yes. So if you see something that looks familiar, then go back to your reference sheet to see which identity can you use. We can substitute in 2 sine of x cosine of x for sine of 2x. And so we have now our right-hand side, which means we've completed our proof. We were able to show that the left side is equivalent to the right side. Okay, so we expanded the left side. We recognize the Pythagorean identity and our double angle identity to rewrite the left side in terms of the right side. And so since the left side is equivalent to the right side, we've completed our proof. Okay, students, so group 1, did we have the same solution as group 2? Let me know in the chat. Yes or no? The proofs do take practice. As we practice different problems asking us to prove the identity is true, we're going to observe different strategies to transform one side into the other using the 10 groups of identities we have learned in chapter 3. Okay, let me see. Great. Thank you, students. Okay, we got the same. Yes. Okay, so there have been a couple of students asking me for screenshots. Remember, if you had to step away for a moment or you missed a class session, I'm always happy to share my screen with you so you can get screenshots of what you missed. We are approaching the halfway mark. In the last 3 weeks, we do have one holiday, which is July 4th. And oh, I did get an email from the VP yesterday that although I think one of our class sessions was designated for Santa Ana College to observe Juneteenth, because the time of our class was scheduled before that, we still do have to meet all this week. So the holiday that we have is the same holiday that's in the syllabus, which is next Monday. So next Monday, there's no school, but every other day, or I mean, Monday through Thursdays, we have our class session. So if you have questions about that, let me know. Let me pause our recording.